Spanning tree. A spanning tree of an undirected connected graph G is a subgraph of this graph G which connects all its vertices using minimum possible number of edges. So this is the important point here, that it should connect all the vertices of the graph using minimum possible number of edges. That is when you will call it as a spanning tree of the graph G. When I say it should have minimum possible number of edges, can there be cycles in the spanning tree? Can you have any cycle in the spanning tree? The answer is no. And why is it? Because if you have a graph like this, these are the vertices of your graph. Let us assume there is a cycle, okay? This graph is having a cycle like this. If this is the case, then if you remove any one edge from this graph, let us say I removed this edge, it will still remain connected. Still, all the vertices are connected by edges. Instead of this, let us say if I removed this edge, still all the vertices are connected in this graph. Which means whenever you have a cycle in a graph, if you remove any one edge from the cycle, the graph will still remain connected. Which means a graph with a cycle can never be a spanning tree. A spanning tree will never have a cycle in it because you can still remove one edge. What is the condition for spanning tree? It should have minimum possible number of edges for connecting the graph. But here, when you have a cycle, even if you remove an edge, it will still be connected, which means it is not the minimum possible number of edges. Because of this, there cannot be a cycle in a spanning tree. The next question is, can you form multiple spanning trees from a same graph? Let us say I have some graph G. Is it the case that I will have only one unique spanning tree of this graph? Or is it the case that I can have any number of spanning trees? The answer is, you can have any number of spanning trees. It may be only one, it may be 2, 3 or whatever be the number. So then the question is, when is it the case that I'll have a unique spanning tree for this graph? See, this lecture is a very interesting lecture. One thing you have to do is, whenever I come up to some particular point, try to engage your brain and try to think what point I am getting to, or just try to think about the scenario and what can happen in this scenario. It will be very interesting because almost every single point that we discuss in this lecture will be something interesting and it will be something that we take out from a graph, right? So let us get back to this point. When is the condition that you will have a unique spanning tree of a graph? Just think about this. You have a graph and you are trying to construct a spanning tree which connects this graph using minimum number of edges. And I'm telling you, there is only one such spanning tree possible for this graph. Then what should this graph be? The answer is, in this case, this graph G should be a tree. When it is a tree, that is the only case when your spanning tree is unique. Why is it unique? Because if these are the edges and this is how you have connected, this is a tree for now. In this case, this itself is a tree, and if you disconnect any edge, the graph will get disconnected, because of which the spanning tree is this tree itself. This tree is a graph which itself is its own spanning tree. So this is the only case where you will get a unique spanning tree, because you can't remove any edge from it and still keep it connected, right? So what did we learn about spanning trees till this point? First thing is that a spanning tree should include all the vertices that are there in this graph. This is the first point. Second thing is, as the name suggests, a spanning tree is always a tree. And what about the number of edges? We already said that the number of edges should be as less as possible. You should have the minimum possible number of edges. But there is something more to it. It is not just that it is the minimum possible number of edges. This minimum is always one particular number, and that number is v minus 1. So always your spanning tree will be having v minus 1 edges in the graph. For example, this we already said is a spanning tree. How many edges does it have? 2 edges. And how many vertices? 3 vertices. So what is the number of edges? V minus 1. Similarly, when we took this spanning tree previously, we had 5 different vertices. If you have 1, 2, 3, 4 edges, then you got a spanning tree, which means whenever you have a spanning tree, it will be having v minus 1 edges in it. The fourth one is that a spanning tree will always ensure that all the vertices are connected. So these are the conditions under which you can say that this is a spanning tree. So coming to the spanning trees, we already said it will be having v minus 1 edges. So the next question is, if I am having lesser than v minus 1 edges in a graph, let us say there is a graph G in which I am having lesser than v minus 1 edges. Then what does this mean? If I am having lesser than v minus edges in a graph, this means this graph is disconnected. This is what it means. Whenever you have less than v minus 1 edges, this graph is disconnected. For example, if we take this same graph which is having 5 vertices, let us say I am having less than v minus 1 edges, that is maybe 3 edges. So 1, 2, 3. So I am having 3 edges. So this graph is having one connected component as this, and this isolated vertex is a separate connected part. That's a disconnected part. So this is a disconnected graph. So whenever your graph is having less than v minus 1 edges, the graph is disconnected, which means no spanning tree exists for this graph. Okay. Next thing is, we talked about what happens when you have less than v minus 1 edges. What if you are having more than v minus 1 edges? If you are having more than v minus edges, that means this graph is having at least one cycle in it. Whenever you are having more than v minus 1 edges in a graph, this is having at least one cycle. And how can you say this? Because if you are having, let us take the same graph, this is presently having v minus 1 edges. If you add one more edge to it, if I make it v edges, it is guaranteed that it will always form at least one cycle. So try to add any edge here. If I add one edge here, it is forming a cycle here. Instead of this, if I add it here, it is still forming a cycle. What if I add here? This is still forming a cycle. So if you add one more edge to the spanning tree, then it will form a cycle. So this means removing one edge from a spanning tree will disconnect the graph because it is having minimum number of edges to keep it, and adding one edge to a spanning tree will always create a cycle, right? So if you take a spanning tree and add back an edge, let us say you had a graph, you formed a spanning tree from that graph, and if you add back one edge which you removed from this graph, then you will form exactly one cycle. That is, if you have a spanning tree, this is your graph, and you removed some edge in order to make it a spanning tree. And let us say you added back exactly one edge. Let us say I added back this edge. In that case, this spanning tree will be having, now it is no more a spanning tree, but this graph, subgraph will be having exactly one cycle. So this is another property. Next thing is, when you're counting number of spanning trees, whenever your graph is having multiple paths between nodes, that is, if you have one node here, one node here, one node here, and let us say to reach this node from here, that is from A to C, if you are having multiple paths, that is, if this is a path, and let us say there is one more path that exists from some other vertex, let us say D is here. if you have another path like this. So if there are multiple paths between nodes in a graph, that means this graph can form multiple distinct spanning trees. So whenever you have multiple paths between nodes, then this graph can form multiple distinct spanning trees. This takes me to the question of how can you count the number of spanning trees possible? If you have a graph like this or any graph, how will you count the number of possible spanning trees? So it so happens that this count or the number of possible spanning trees actually depends on the structure of that graph and also the number of vertices that are there in the graph. So what we'll do, we'll explain about a complete graph. If you're having a complete graph, let us call it Kn. If it is a complete graph, then you will be having n power n minus 2 spanning trees for this graph. This is called as Cayley's formula. According to Cayley's formula, whenever you have a complete graph Kn, the number of spanning trees possible is n power n minus 2. This is Cayley's formula. And if, let us say, a graph is not connected, okay? If a graph is not connected means all the vertices are not connected together in the graph. Maybe one part this is connected, these two are also connected, but this is a different connected component, this is a different connected component of the same graph. So if your graph is such that it is not connected, then it does not have a single spanning tree, but instead it has multiple spanning trees for each of the component. So you are having two different components here. For this component, there may be one or more spanning trees. Similarly, for this component also, there may be one or more spanning trees. So the point is, you can have a single spanning tree only for a connected graph. When it is not connected, then for each of the connected components, there may be separate spanning trees, but the whole graph cannot have a spanning tree if it is not connected. So this is about a graph which is not connected. Now let us get back to connected graph. In case of connected graph, let us say it is having v vertices and v edges. If this is the case, what can you say about the number of spanning trees? If you are having v vertices in the graph and this graph is also having same number, v is the number of edges, then how many spanning trees will this graph have? In this case, the answer is it will be exactly v spanning trees. Why is it exactly v spanning trees? It is because if you draw it and understand, it will be easier. If you have let us say you have these are the vertices of your spanning tree. If this is the case and you have exactly v edges, so 4 vertices are there, I am drawing 4 edges as well, okay? 1, 2, 3, 4. If I am drawing 4 edges, then when you remove any one vertex, any one edge, it will become a spanning tree. If I remove this edge, it is a spanning tree. Similarly, if I remove this edge, it will be a spanning tree, which means when I remove any one edge, that will be a spanning tree of this graph. So I am having a total of v edges. I can remove any edge to form a separate spanning tree, which means I have v different spanning trees possible for this graph. That is when it has v vertices and same number. V is the number of edges as well. One more point. This is interesting. If you contract an edge in a spanning tree, what is contraction of edge? Contraction means you are kind of removing this edge, or you can say you are merging two vertices. If I A, B, C, D, these are the different vertices I have. If I contract edge AC, what happens? The vertex A and vertex C will merge, which means this is my new vertex AC, and there is no edge AC which is present. AC is now a vertex, okay? And B will remain as it is. D will also remain as it is. This is what you call as contraction of an edge. You contracted edge AC. Now A and C are the same vertex. In this case, whenever you contract an edge from a spanning tree, what you obtain is a spanning tree of the contracted graph. That is, this is, let us say, your actual graph. A, B, C, D is your actual graph. And this graph, let us say, has a cycle. This is your graph. In this case, if you contract the edges of a spanning tree and you made this, what you obtained is the spanning tree of the contracted graph. That is, instead of this, in the original graph itself, if you contracted AC and you made it a single vertex, then whatever be the remaining graph, if you take a spanning tree of this graph, let us say by removing this edge, then you get the same spanning tree. So by contracting edge of a spanning tree, you obtained spanning tree of the contracted graph. So these are basic properties of spanning trees. In the next lecture, we'll be talking about minimum spanning trees, MST. So MST is a very important concept. It is used in multiple algorithms and all. So here we explained about what is spanning tree and what are the properties of spanning tree. When we go to minimum spanning trees, whatever we discussed here about spanning tree, everything will hold. Along with that, there will be some additional properties that we'll get when it is a minimum spanning tree. So in the next lecture, we'll see about minimum spanning trees. One more thing before we conclude this, where will we actually use this concept of spanning tree? Where is it used? So it is generally used in computer networks or maybe theoretical mathematics, optimization, these sort of things. Whenever you want to know that which is the minimum cost connection between all the nodes possible, this is one situation where you will generally use a spanning tree.